Welcome back, everybody. So now that I've presented the logical model to you and how we can slice, dice, aggregate, roll up, drill down, pivot, and so on, I'm going to say a few words about the implementation. High level, I mostly want to focus on an implementation in SQL. But on the high level, you have two main paradigms for implemented data cubes, OLAP cubes. One paradigm is called ROLAP, the other one is called MOLAP. In fact, the idea here is very general to any data shape. When you want to implement a system for any data shape, you can either do a native system, that's what Neo4j is for graphs, that's what PostgreSQL is, to SQL, that's what MongoDB is, to trees, so you can do it natively, or you can cheat and put yourself on top of another system. For example, you could implement, it's hypothetical because who would do that, but you could implement a relational database on top of MongoDB. You just store the tables as flat trees, right? Likewise, you could implement also a graph database on top of a relational database, like a triple store. You could put every triple in a table with 3 columns, right? So you can either do it on top of another shape that, of course, you would need to nicely encapsulate and hide from the end user because of data independence, or you can do it natively. MOLAP is kind of it means multidimensional. OLAP is kind of the native implementation for data cubes. It also allows some sparsity in the process. ROLAP is the cheating version where you just put yourself on top of tables and you compile everything to SQL. So this is called ROLAP. It's a relational OLAP. And I'm going to focus on ROLAP. I'm not going to talk about MOLAP, but just know that it exists and it's a completely different implementation, entirely native. Why ROLAP? That is actually the reason why the startups that basically came up with OLAP cubes in the 90s were purchased by relational database systems companies. It's because a fact table like this that represents a cube can in fact be stored as a relational table in a SQL system, right? This is the idea where it's very, very natural to store a cube like this. However, what's very important is that it's still a cube on the logical level. What you see here is only a physical implementation as a table of the cube, so that is the visualization. But remember, it's still a cube. You have to keep it in mind. It's not a table. And so the way that you store a cube as a table is 1 column per dimension, 5 of them here, and then a column for the value at the end. Now, there is another approach that some people take with several value columns. Not just one, but several. And these value columns basically share the dimensions. It means that for all of this combination of dimensions, it's a specific position in the cube, you can specify multiple things, and these things are called measures. For example, you could say that for Digetec Galaxus in Switzerland for the year 2024, then the revenues were such, the expenses were such, and the profits were such. Right? So these are what the measures are, and they all have in common the combinations of dimension. And then for another year, another company, and so on, then you would have different expenses, profits, and revenues there. For whom is that clear? Right? So this is called a measure. That's a word you will find in a lot of data cube software. But in fact, it doesn't matter because it's the same. And the reason it's the same is that you can basically convert one into the other. The transformation is called pivoting, pivot, unpivot, and there are even extensions to the SQL language that do pivot and unpivoting. It's actually quite simple. What it does actually is that when you have multiple columns like this, like revenue and profit, it's the same idea of taking these eight cells and you just stack them again like this. You just put them on top of each other and you add a column here that you can call measure or concept or whatever, and then you say revenue, profit, revenue, profits. So you see what happened here. These headers here, revenue and profits, are basically transformed into members of a new dimension that we call measure. But these values are exactly the same, right? Who sees that it's the same thing, that we can transform one into the other and back? Okay, very good. So this is called pivoting and unpivoting. That is the reason why I'm only going to show you with 1 column, because you can just always transform it into just 1 column. Okay? The next thing that you have in the rollup implementation is that you have satellite tables. Yes, there's a question.
So is the previous thing also the same if you have different data types, like pivoting and?
That is an absolutely valid question. What you would do if you have multiple data types is that you would basically use a special type that it's not in every database. You would have a variant. You could call it a variant type. Another possibility is to just partition your data by types, meaning that you only put together what's the same type, so all integers, all strings, and then sort them in separate tables. But the most straightforward way to basically force this to work, even if the types are different, is a variance type. That is basically a way to have polymorphism, right? Which in this lecture we've seen a lot, right? So the idea of having a messy data that doesn't have a schema, right? Does it make sense? Right? So a variant, you would have a variant column in here. Okay. All right. So now what you typically have around the fact table are satellite tables, typically one satellite table for each dimension. That means that these members that we have in here below the dimensions are in fact nothing else than foreign keys that point to the primary key in some satellite table, right? Here, we just point to satellite tables. In other words, you can do joins between the satellite tables and the facts table in this way. For whom is that here? Right? Who loves to normalize data in there, like third normal form, fourth normal form, fifth, sixth normal form? Do we have any raised hands? Nobody? Oh, I'll still show you a slide, but maybe you'll not love it as much. But for the people who really love normalization, we have the snowflake schema. So if you're not happy with just having these satellite tables and you want to further normalize them, then you can apply these transformations to split them even more. That is the snowflake schema, right? I suspect that is one of the reasons why the company with that name is called that way, right? It's a hint to this. So star schema and snowflake schema. Who loves to denormalize data? Ah, okay, very nice. Let's denormalize data then. So if you're not happy with this, so that's the highly normalized data with separate tables, like here I have a town going to the country, going to the continents, and you think that's an overkill, that's too complex, then you can do the opposite. You can basically take all your satellite tables and then squeeze them into the fact table. What you get then is a denormalized fact table. So now, for the same dimension, not only do you have the original member, but you have all the columns that came from the satellite table. Because again, you do a join with the satellite table to denormalize. And then you get that. An example is if I denormalize my facts table for the geographic dimension, and I had my city that was my basically my original value, and then I join it with this here. What I get is an additional country and continent column, but they're not other dimensions. They are the same dimension, it's just additional data. And now you see that we have redundancy. Switzerland, Europe, 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 Asia. That's how you see it's denormalized. How you also see it's denormalized is you have a functional dependency from the city to the country, and you have a functional dependency from the country to the continent. How do I see it? Switzerland is all in Europe. That's a functional dependency. Who sees that? Right? So this is the reason why, in that case, my facts table is not denormalized. Why would I want to do that? Well, first, because I love denormalization, but there's another reason. You can actually take this kind of fact table, which is then a single table, put it in a CSV file and import it into Excel or spreadsheet software. And then what you can do is select it entirely, menu, data, summarize with pivot table, and then you have a very nice, I'm not going to call it an Easter egg because this is an actual feature, but then you end up in a user interface that allows you to drag and drop your dimensions to dice on the row, dice on the column, slice, and so on. And that's really, really convenient for a lot of use cases. And so this is why this kind of denormalized fact table is very, very practical in real life to do quick analysis with spreadsheets. Okay, so now that we've seen that, that's how we map these cubes to tables. And again, you see how what was a tree below a dimension, you have a hierarchy, that's a tree. But I represent that tree not as XML or JSON or whatever. I represent it with functional dependencies in this way. This is how I represent my hierarchy of cities. Okay, let's query some data then. Well, there is a language for data cubes. It's called MDX, multidimensional expressions. But you have already been put through so many languages and syntaxes in the lecture that I'm going to spare you the teaching yet another language. You don't have to worry, I will just show you one or two slides, but that's it. Instead, and that's the reason I'm focusing on OLAP, we're just going to use good old SQL. We are basically just going to implement with SQL on the facts table these slicing, dicing, aggregation, and so on. Okay, so again, do not worry about MDX. You don't have to learn it. All right, so now imagine that I have this data cube that is represented as a facts table. So it's a relational table in PostgreSQL or whatever system you choose. And I have these satellite tables, and you notice that all of these, for example, are foreign keys that point to this primary key. Then you have the year, the quarter. All of these are foreign keys. Of course, in real life, you would have references, not names, but that points to here, right? And then you have the brand and the price. Then you have the customer. Of course, here you have a customer ID in real life, but that points to address, phone, and so on. Okay, so these are the fact table and the satellite tables. Now, obviously, if you want to do something useful in SQL, you can join the satellite tables with the facts table. And that you know how to do, right? How do you join in SQL? You just put them all in the from clause. Let's say we join the facts table with the satellite table for the time. And I have my join predicate. So I join on the fact that the date, so basically this, must match this. This is my joining predicate. Okay? For whom is that clear? Right? That's just a join. And now I basically replace the date with the year. Okay? Okay. For this reason, because it's just a join, I'm going to just now drop the satellite table. I just get rid of it. And I'm just focusing on one single fact table, and everything is in there. And it's a normalized fact table, meaning that I will not have multiple columns for the same dimension, right? So one column per dimension, no satellites, just plain and simple to focus on that. So this is what I'm going to take. This is my facts table. I have the year, the brand, and the customer. I only care about the values that are in there, no satellites, and this is my quantity. What are the dimensions of that cube? Can anybody tell me? Yes? 3 times? 2 times? 2, exactly. And that's a counterexample to, you asked the question, right? That was you. So this is an example where it's not the same number of members in each dimension. Okay, so 3 times 2 times 2, and we have 12. Okay, everything is all right. That's 12. Now, if you want the complete view, well, you could just use select star, right? But I just explicitly put the columns, and then you get the entire facts table. If we want to slice, what am I going to do in SQL to slice? Where exactly? And that is a selection. Exactly. That's how I slice. So you see, it's straightforward. This is why it's so easy to actually implement cubes as tables. Slicing is done on the fact table with a selection on the fact table. And then here I'm basically slicing on the year 2017. But that's only physically a selection. Logically, what is really happening is that I have a 3 by 2 by 2 cube, and I'm taking a slice of it, which is a 1 times 2 times 2 subcube. Who sees that? Who doesn't see that yet? Who sees that? Okay, awesome. So this is slicing. I can slice even more. What if now I want a 2 by 1 by 2 1 by 1 by 2 subcube? So now I also slice on Samsung. I'm slicing in 2 dimensions. And yeah, so that's how you slice. You just add your basically predicate, dimension equals member, to the where clause. Okay. Now let's get back to the complete view. What about if I want to roll up some dimensions? Roll up here is all or nothing because I don't have hierarchies in the dimensions. It's all flat, right? I just have 7, 16, 15, that's flat. Apple, Samsung, it's flat. Peter, Mary, it's flat, right? So when you roll up, it's just all or nothing. Either you have the details or you don't. So what if I want to aggregate and forget about the details, let's say for, I don't know which one I'm doing on the next slides, but let me say for across the customers, right? I have a year and a brand, and I want to aggregate on the customers. What SQL clause do you think I'm going to use? I see raised hands here. Group by, exactly. You do a group by. Group by on what? Exactly. You group by anything that you do not want to aggregate on. Very precise. So thank you for this. That's exactly the idea. You put in the group by everything except what you want to aggregate. So the group by basically protects against the aggregation, right? And then you aggregate on the rest. So indeed, if I want to aggregate on the customer, then I just group on the year and brand. And then I have, as you know, you always need to always put your group by keys also in the projection. That makes sense. And then we aggregate on the quantity. It's a sum, but it could be an average, a mean, a max, a count, anything else. You see what happens here? Now I merged, for example, these two. 1 plus 5 gives me 6. So now what happens is that this was a 3 by 2 by 2 cube. This is now a 3 by 1 by 2 cube, 3 by 2. But what happened is that I didn't slice here. I squeezed along y dimension to sum over the customers. Who is with me? Right? And this is with a good old group by. It's not even new to you, right? So just a group by. Now, if I want to roll up even more, what do I need to do? You probably saw it quickly. What if I want to roll up on the brands too? Not just the customer, but also the brands. What should I do? Do I need to add it or remove it? Yes? Remove it, exactly. I remove it from group by. Removing from the group by is going to roll up entirely that dimension. And now I just have the year and the quantity. So now I squeezed my cubes in 2 dimensions and I have only 1 dimension left. If I want to finish squeezing it, then I just drop the group by. And you know that if you just aggregate without a group by, it just aggregates to a single value, like the total sum of everything or and so on. Now that is the fully rolled up version. I rolled up all my dimensions in here. Who is with me? Okay. So you see, we have everything we need in SQL. The opposite, if I want to drill down, then I add back to group by whatever I want to drill down on, right? So I just now go back to my year and brand. Okay. Do we have everything we need in SQL? Well, yes, we do, but it's not necessarily going to be convenient. Now think of the use case where you want to compute the subtotals and the grand total. So you have the year and the brand, let's say, like this. And now you want to also have a total on the years for every brand, a total on the brand for every year, and a grand total on everything. Well, we already know it's 34, right? The grand total. How could I do that? Basically, I want a SQL query that generates all the data necessary to my cross-tabulated view with my 2 subtotals and the grand total. I saw some raised hands. Who raised their hands? Anybody, any idea? On Zoom, maybe? Okay, let's start with a naive ID then. Why don't we write the queries separately? So I have a first query that gives me the values that are the actual values per year and brand, right? So these are the query in the most of the numbers in my cross-tabulated view. Now, what if years are basically on the columns and brand is on the row? Then that would be the numbers at the bottom, the subtotals for every year, the subtotals summed over the brands. This would be the subtotals on the right. If I aggregate across years, and I have a subtotal for Apple and a subtotal for Samsung, and this here is the grand total, right? Who agrees that these 4 queries, if I execute the 4 of them, that gives me the numbers for my cross-tabulated view with the grid of subtotals and grand total? Who agrees? Who doesn't see it yet? It's fine if you don't, right? So let me show you again what I mean with the, should be somewhere here. This one. Basically, that's the data that I got after I basically aggregated, just another example, but I basically did an aggregation to get rid of the customers. Well, don't want to get rid of the customers of the company, but aggregate over the customers. And then that gives me 4 values. This was my first query that gives me these 4 values. The second query gave me these values, basically aggregated across the salesperson, but once for every year. The third query gave me these 2, right? Aggregated for all, so it's not all times, but all brands in my example over there. and then the grand total, that is the aggregation. So basically what you need to see is that I need 4 SQL queries for that. One for here, one for here, one for here, if I can operate at the right place, and here the grand total. Who sees that this here gives me exactly what I need. Awesome. So this is the idea. These are my 4 queries. Now, what if I want a single query? Does anybody see a way of doing that in a single query? Complex query, but single query. You take a union. What is in the way of the union here? Exactly. So indeed, we need to do a union, but you see that the columns are not the same. The attributes are not the same. How can I get the columns to be the same? Yep. And what do I put in the cells that don't have anything? It's the right idea, but what do you put in the empty cells? Can you have empty cells in SQL? I see nodding hands. What do we put in empty cells? Nulls, exactly. That's exactly the idea. So you're absolutely correct. This is a union, and we need to make it fit. Basically, you see, union, union, union. But I need to add a null here, and 2 nulls here to make it fit into this table here. You see now, I have my first 6 in here, then I have my subtotals by year in here, then I have my subtotals by brand right here, and I have my grand total null, null, 34. Who sees that? I just took the union, right, and padded with nulls. Now, it's a bit complex, right? If you have to write this every time you want to populate such a view, it's cumbersome. But there's a solution. There's a better way, and that is due to an extension of SQL that PostgreSQL and others introduced. It is called group by grouping sets. That does the same thing. It basically is a union of different group bys, and you say, okay, I want the year and the brand, then the year, and then the brand, and then the grand total with nothing. You see that these 4 lines here are exactly the 4 group bys, right? So that's group by grouping sets. It is just equivalent to a union of 4 group bys. Who sees that? All right. But now I have even something better, because even that I'm too lazy as a computer scientist to write, but there is a structure in there. Do you see that this is the power set of year brand? These are all the subsets that you can have under year brand. Who sees that? Okay, so we say group by cube, like this. Group by cube, year brand, that does exactly this. Okay, so this was an extension that came later into SQL and PostgreSQL and many products, because they have the data cubes in mind, and they have them in mind so much that they actually explicitly write cube in here. Okay, great. And that gives you this. If I take all of these numbers on the right and I display them in my view, this is what I get. Okay? So that was the SQL query that gave me the numbers to put in there. Now, SQL did not give me the view. SQL doesn't know anything about cubes or even about cross-tabulation. The only thing that I can expect from SQL is that it gives me the numbers that I put in there. All the rest I need to do separately, maybe with Python or whatever language I want. And this is where MDX comes into play, because MDX allows you to directly say that you want the view. Okay, but we are not talking about MDX. So, and then you can play and imagine the SQL query. If I want to now go to Peter instead of all customers, then I would just add a where clause, right? Who agrees? In SQL, I just say where customer equals Peter, and that would give me these new numbers. All right, and what did I do here? I pivoted, so I say now where period equals 2017, and here I would have a group by cube. Group by cube what for generating this? Group by cube. Brand and customer. Group by cube, brand, customer. Exactly. And where period equals 2017. Now, trivia question. Group by cube needs to be 2, could be 3, could be 4. So if I have n attributes in group by cubes, how many grouping sets do I get? 2 to the power of n. You're computer scientists, fantastic. So this is the power set, so 2 to the power of n, exactly. So here it's 2 to the power of 2, but that works for any one of them. Okay. Now, let's move to the next bit more difficult. What if we now have these hierarchies of dimensions, and I have my denormalized fact tables, and now I have this whole town, country, continent, world, and so on. So this means that what I want to do in essence is basically to have my numbers per city. And then I also want my numbers per country. So that's kind of separate where the city is not there. And then the numbers by continent. So these are my subtotals now, but these are not subtotals for a dimension. These are subtotals within a dimension. These are intermediate subtotals per country, per continent, and so on. And then I will have my grand total on the whole world. Do you see that we can do the same here, pad with nulls? Like this. Who sees that? Right? This is how we can extend the fact table with nulls, and now we can have the values that have my subtotals. Okay. So let's take this example here. It's just a different use case. Instead of my countries, now I have quarters and years. So you see how I have a Q1, Q2, Q3, Q4. This is how we call the quarters in accounting of 20, then of 21, then of 22. Right. So for just for those of you who might not know, in accounting and typically on the most of the market authorities like the SEC, they require companies to file their reports, balance sheet, income statement, and so on every 3 months. And so we say Q2, Q3, Q1, Q2, Q3, Q4. All right. So now, if I do it in SQL, this is what it will look like. I basically have my denormalized fact table with year, quarter, and so on. So these are the columns that belong to my hierarchy in that spirit here, like I had continent, country, city, but now it's year and quarter. So I need basically for every quarter, so group by year quarter, that gives me for every quarter. Then if I just say group by year and I remove quarter, that is going to do a partial roll-up and gives me the aggregated value per year. And if I drop here completely, now I get the whole all times periods. Right. Of course, to simplify here, I assume I didn't have other dimensions because, of course, it makes the query more complicated. But I wanted to show you this, that essentially what I get is all of my values per quarters. So this is basically all the blue headers here, not this, not this, and not this. So this is my first query. My second query gives me the subtotals per year. So in my view, that would be here, here, and here. And then finally, the grand total on the right. Who sees that? Now, what is key to see here, and the difference with before, is that nowhere do I have just group by quarter. That I don't have. Do you see that that's the difference with before? Because before I was talking about different dimensions. So I wanted to have all combinations. That's what the power set. But now I'm talking about one dimension, but it's the hierarchies within that dimension. The years, the quarters, maybe I would even have the months, the days, if I wanted to be even have an even more elaborate hierarchy. So it's very similar. I can also pad with nulls. I can also take the union. I can also put the grouping sets, year, quarter, and nothing. But I do not have quarter alone, okay? Because this is a real roll-up, step by step on the same dimension. There is also a shortcut for that. If you don't want the power set, but you just want to basically go from the right to the left, like this, this is called group by roll-up. Group by roll-up, year, quarter, gives you the grouping set. Year, quarter, just here, and nothing. It's basically going right to left, wiping out from the right to the left. Trivia question. If I have n attributes in group by roll-ups, how many grouping sets do I get? N? Any other idea than n? N minus 1? Any other ideas? N plus 1, yes, that's the one. You see there's 2 here and that's 3 grouping sets because you need to have the empty one as well. Okay, so you see that's linear. Group by roll-up is linear and the group by cube is exponential. Okay. So this is it. This is how you do it in SQL. And you saw this extension, group by grouping sets, group by cube, group by rollup. This is made for OLAP cubes. Now, just so you see, you don't have to learn it. Don't worry, no language to learn. But it looks like this. So they use these square brackets along the dimensions and members. it looks like SQL. Many people actually start their languages making them look like SQL. So it has a select and a from, except that here it's not a table, it's a cube. This is a cube. What is also not in SQL and that you have in MDX is on columns, on rows. This is dicing. You're basically dicing on the measures. So that would be revenues, profits, and so on. So that would be the accounting hierarchy. And on the rows, you would have the location, so all the geographic locations. So this is how you dice. This is how you slice. You would just add a where clause. Also in MDX, that's a where clause. And here you slice, for example, on the sales of MacBook Pros, right, as an example. Okay. Just so you see how it looks like. There is a language called MDX, and it's able to dice and slice and aggregate and so on. And it looks cosmetically, it starts by looking like SQL. This is it. Don't learn MDX. By the way, at the exam, I'm just repeating, you will have PostgreSQL, PySpark, Spark SQL, or data frame transformations, and JSONic. All the rest, it's not going to be practical programming questions, just on your screen, right? And you really need to focus the learning on PostgreSQL, PySpark, Spark SQL, and JSONic. Is there a question?
We stated that we want to have a read-intensive, we stated that we want to have a read-intensive system differentiating ourselves from OLTP. Then why do we use SQL to implement this?
Oh, it's read-only SQL. SQL is not writing anything, right? But why do we use SQL? I think the best answer is because we can. I will say because we can. Again, we are just cheating. We are just saying, okay, we want to implement a data cube system with a language and so on. And because the facts tables give us a tabular representations of the cubes, we can just cheat and compile everything to SQL on facts table and only implement the difference, like dicing that SQL doesn't have. Does it make sense? SQL, in fact, can also be good at OLAP if you don't insert or delete and so on, and you put a denormalized table into a SQL database. You can absolutely write group by queries and sort and so on and so on. But if you specifically want to have queries optimized for data cubes, you might want to physically enhance the implementation of SQL for that. And an example of enhancement of the implementation of SQL is this. When you see this, the group by grouping sets and so on, this here is specifically made for cubes. And that is an example of the way that the physical implementation of SQL was probably rewritten in order to do that efficiently. And you wouldn't have that otherwise, right? Does it make sense? And it's not the only way. You can also implement a completely native system if you want. There is even an implementation on top of Spark. You can even do that on top of Spark, where you put your fact tables in Spark SQL, for example, or if you have massive amounts. Okay. All right. We have a few minutes left. I'm going to finish with syntax. Because we've seen that you need syntax to exchange information. Why do we need syntax for data cubes? Well, again, one of the use cases is the financial reports. The companies are required to file financial reports in pretty much every country in the world, or almost. The companies have to do that. There is a reporting authority, and they have to do that. In the EU, the banks have to submit risk reports to the banking authority. In the EU and also Switzerland, actually, companies are now required to file sustainability reports, also in an electronic format readable by a machine. These sustainability reports will, in practice, have to be done with XBRL, which I'm going to show you now. It's basically a syntax for data cubes. And basically, the filers, so the companies, produce documents in that syntax, and they upload it to the website of the reporting authority, or in the case of sustainability reports, on their own website. So the Swiss law, for example, will say that the companies must upload somewhere on their website a sustainability report in a format that is machine readable. So this is why we need syntax, right? In the end, it's going to be a zip file with that syntax. In the EU, so XBRL is the name of the syntax, but the EU has a marketing name called SF, European Single. Every time I want to give what it stands for, European Single Electronic Format. ESCF. Who ever heard of that one? Right. So this is a mandatory format for use in the EU for now with companies and soon also sustainability. And it is basically made by the European Securities and Markets Authority, which has its seat in Paris. And basically what they want is an electronic format of such financial reports. And what you can see here is basically a hierarchy with subtotals. Turns out to be a balance sheet here. But do you see here that this is just a hierarchy of dimension members? Right? Who sees that? Just because you have subtotals and so on, and you have the grand total over here. And here you have a dice, we dice on the columns on the period. So this is for the year 2019, and this is for the year 2018, right? So this here is a cross-tabulated view that accountants have actually been using for thousands of years. Actually, even on clay tablets, they were already doing that sort of things. All right, and this is in fact a data cube, and this exists in the XBRL syntax. So it uses all kinds of technologies. This is how actually it looks like in the case of the European Union, that the companies, of course, companies love to have a fancy looking report, right? That's basically either the big book that they send you at the end of the year, the yearly report, or it's a PDF, shiny and fancy. So in order to allow the company to use their shiny and fancy PDFs, but still be machine readable, what we do is that we say, okay, instead of PDF, just use HTML. In HTML with CSS, you can do beautiful presentations. It looks very, very, very nice. But inside that HTML, you also add tags that basically tell you in a machine-readable way what the numbers are about. So for example, one of the numbers that appear here, this is HTML. This is an HTML table, but with CSS, it looks beautiful. Every number here is within a tag that is an XBRL tag, inline XBRL, in fact, and that basically says that this number corresponds to profit loss. So this is here a measure. We call it concept in XBRL for a specific context. So a specific company, period, and so on, and a specific unit, which I have no idea why they did. It's just euros, right? But somehow instead of saying euros, they want this fancy ID, but whatever. Okay, so profit loss in euros and for a specific context. So the context look like this. For example, you have the company, so that would be an identifier. Here is the US. That's called the central index key. So that's the identifier of Coca-Cola. It's the real one, by the way. It's really 21344. Here you have the date on which a number is valid. And somewhere you have the units. It's an ISO standard, but basically the 3-letter. And all of that, basically the unit and the context, is what basically is referenced from here. So you see that every number, every one of these numbers right here is tagged with the dimensional coordinates within the cube where they are located. This is how a machine can actually read that and actually give, and you can use Python or whatever you want to analyze that data without having to automate reading the PDF with ChatGPT. Right? You can directly, really in a high quality, access the values. So this is why we mean what with machine readable. This is a more ancient way of doing that, where it was not inside HTML, but just as a list of facts. So just that's what's been going on for now 15 years in the US with the Securities and Exchange Commission. But now the Securities and Exchange Commission also accepts the fancy HTML filings, right? So it's also perfectly fine now. All right. So yeah, we have what I want to show you here is just that this is XML, in fact, if you look inside. And one of the reasons why I want you to spend some time learning XML and JSON is that because they are used so heavily in even more complex technologies, if you want to keep your sanity with that, XML and JSON needs to be second nature to you. You really need to know for your future in general, at least all of you who will work heavily with data, you must be in a situation that XML and JSON are so intuitive that it makes it actually doable to learn some other technologies that are on top of XML and JSON, right? So this is a definition of the assets, for example, and so on. I have plenty of useless slides that I have here. Yes, we also use XML to connect the arcs. Oh yes, what I wanted to show you is that because it's machine readable and every number is tagged with the coordinates within the cube, a computer can reconstruct views on top of that. The SEC calls that interactive data. So it's a beautiful term. And interactive data basically means that this is the reconstructed view. The company never did that. The company just filed in XBRL these numbers right here, tagged with the context, all the dimensional coordinates. This here is entirely reconstructed by the SEC's computer systems. Right, so this is the idea, and that's fully machine readable. You can analyze it. Okay. All right. So do you have any questions? I'm actually done. You don't have to learn XBRL, by the way. Just also to be clear, I just wanted to say it exists and it's on top of XML. Any questions? A small recommendation to you, if you want to exercise on that. Try to take some facts table, denormalized possibility, as CSV, open it in Excel or any spreadsheet software that supports that, and select it, data summarized with pivot table, and try to drag and drop the basically, let me show you here. So this is the sort of things you can do in Excel with that feature. You can configure, you just need to drag and drop customer here, you drag and drop brand here, you drag and drop period here, you right click, you select 2017, you can do it all very visually. This is the most intuitive way you can learn slicing and dicing. Try it, really try it. This is very practical. Okay. Any questions? Really no questions? Okay. Well, I have a surprise for you. Is that I re-uploaded a new version of the textbook. It has a new chapter 14. It's almost done. I'm basically 2/3 through. It contains what I've told you today, basically. But now you have the textbook version, and I'm really trying to expand the textbook so that it covers everything. So if you want to read it instead of listening to me, then you can look at the textbook. That's it. I'm going to let you go with 2 minutes in advance. Tomorrow, guest lecture by Oracle. Just come and enjoy. Vector databases, the 5th shape. And next week, we'll have this big quiz game and wrap up. It's just, again, celebration of the end of the semester. Thank you very much, everybody. Enjoy your evening. See you tomorrow.